So on the test review, I didn't do a whole lot with this particular section. I just basically did one problem that was kind of exponential, and then kind of led you into a logistic idea. And the logistic idea comes up in the activity or project thing too. So anyway, I'll go through some of these things with you so that you kind of can, use them on the assignment. So they have this, they call this unlimited growth formula, which is on page 350. They use it with cells, but you could use it with anywhere. And this is the formula that they use. Okay, so it says that, of course, n sub 0 is the initial value, just like with an ordinary exponential equation. All right, the a value is always the initial value here. Okay, E is just E, and kt is some sort of, well, t is time, but k is some sort of a rate. All right. So they have an example 1 here, and it talks about a colony of bacteria, and they give you the formula. Or the equation, I should say. So I mean, it's not like they're just kind of giving it to you, and then you just got to manipulate it, right? So it says determine the initial amount. Well, that's easy. That's just going to be 100, because that's always that a value there. So let's see if we get something. What is the growth rate? Well, and k is the positive constant that represents the growth rate. So the growth rate is 0.045. Unless they want it as a percent, 4.5%. C, what is the population after 5 days? So we would just go ahead and figure that out. So you just put that into decimals and let it figure out. How long will it take for the population to reach 140? So that's going to go here. So all these, I mean, once they give you the equation, it's just manipulating it. It's not a whole lot different than what we just did up there, what we did before. You did in the assignment. Like for this one, divide by 100, take the natural log of both sides. Okay, so see, I mean, these problems aren't going to be really that much different than what you've already done. It's just that they're modeling it so that there's different models. So like this one is a growth model. All right. The other one here is Newton's law of cooling. Which is this. And these are U's. This is on 352. So again, so T is a constant, is a temperature that surrounds, that's what they use, what is being measured. So, and we'll do something like this after break. So basically what they're saying is, let's say that, you know, a number of you have some drinks in here, okay? So whether you've got something hot in there or something cold in there, all right? You have it sitting on your table and you're drinking from it and stuff. So the temperature of this room would be T because it's affecting your drink, right? You know, even if you have one of those, oh man, my students have a lot of them. I can't think what they are anyway. Yeah. I mean, those things are pretty dang good, right? Yeah. So you're not going to get a whole lot of effect out of that, right? That's why they're the way they are. Okay. But if you just got a regular old, you know, water flask or cup from Arby's, you know, it's sitting in this room and it's getting affected by whatever is in there. Okay. So that's what T is. Okay, so T would be like the temperature of the room. Okay. U is the initial temperature, U sub O. And, okay, I got T already. And E is E and K is a rate. Okay. A negative constant, they're calling it. But it's usually some sort of a, stands for some sort of a rate or something that's going on there, okay? And T is time. All right. So let's see if we can find. So I'm just looking at one of the problems on your, I don't know if it's on your slide or not, but on page 357, number 13 is a perfect example of Newton's law of cooling, okay? So let's do that one. So it says cooling time of a pizza. So a pizza baked at 450 degrees is removed from the oven at 5 p.m., placed in a room that's constant 70 degrees. So T is 70 there. All right. And after 5 minutes, the pizza is 300 degrees Fahrenheit. After 5 minutes. What temperature can you begin eating it if you want it to be at 135? So let's use Newton's law of cooling to figure this out. So let's see. It was U sub T equals the big T. So what is that? 70 degrees, right? Because they take it out 70 degrees. Parenthesis, or plus, excuse me. Parentheses, U sub O, that's the initial. So what is the initial temperature? 450. Minus, I think, right? Minus big T again to the KT. All right, so that's what we got. So we don't have enough information to solve the problem because what are we missing? Oh, did I not put E in there? Dang it. I'm missing E. But what are we missing here? Well, t is time. That's what we're going to solve for. K. K is the thing we don't know.
Is that our negative constant?
Is it say negative K?
It says K is a negative constant. Yeah.
Oh, it just says it's a negative constant, but it doesn't. Yeah. Okay.
But yeah, I guess it could be positive. Right?
Yeah. Well, it just basically tells you that what you get for K is going to be negative, and that's going to be okay. All right. So here's a Newton's law of cooling problem. We don't know what K is, but we can find it by using this information. Okay? Where's the 300 going to go? Where would we put that 300?
What the initial temperature, the rate formula, take 450 minus 300 over 300.
No, what does U of T stand for? What does that stand for?
Well, that's the final temperature, right?
Well, that is the temperature, right? At time whenever. Okay?
So we can put 300 at the 5, right? And then solve for T.
Well, let's put, yeah, we're going to put 300 right here. Okay? Put 70 there. 450 here. 70 here. We got E. We don't know what K is, but we do know it took 5 minutes to get to that temperature. All right? So we're going to put 5 for time. Okay, so let's figure this thing out. What should we do? Yeah, let's get rid of the 70.
We divide by 450 minus 70.
Let's do that. I need help there. 23 divided by 38.
.605. Yep.
Point what?
0.605.
Okay. Now what?
Take the natural log.
Yeah, I mean, again, it's not like, it's very similar to what we just did in the last, that 4.5 section, or, yeah, 4.6 section. So now we got to take the natural log of this, natural log of this, right, which is the same thing as putting the 5K out in front. So what are we getting?
Negative 0.1001.
Negative 0.101. Okay. So now we know what K is. So now we can do anything the problem is asking us to do, right? So we have U of T equals big T, which is 70, plus 450 minus 70. No, minus 70 to the E. Now I know what K is. Shrink this down a little bit. Negative 0.101 times T. Okay. So now that we know what K is, we have an equation or a model. We can answer any question. They wanted to eat it at 135. Where are we going to put the 135 at? Yep. And we just got to figure out what T is. And we could graph this too, and we could have got an answer. Natural log. And there we go. So we'll get a time. Okay. Does anybody get it?
$17.486.
Yeah, it says about 518 in my book here. So I guess that's pretty close. There we go. So that's Newton's law of cooling. All right, and we just set that. You just put the numbers in and solve it. Again, it's just really, once you have the equation, you're not doing anything different than what you did before. Okay.
So once you solve for k, that's the constant.
Yep. That's the constant. Yeah, that makes it work.
Yeah.
You gotta have k.
I know some of the physics equations, k usually is a constant number, or you don't really solve for it.
You mean they just give it to you?
Yeah.
Yeah. Well, mathematicians want you to figure something out. Physics people said, here, just give it. Here's a constant. Just run with
Yeah,
it.
here's a constant.
Just run with it.
Don't do that extra math.
Yeah, who wants to do the math stuff? I know you might be getting a little antsy, but so before I do the one thing I want to do with you, they talk about a little bit about a limit to growth, and this one comes out on, it makes sense to look at 24, I guess. So if we have a population, usually does something like this, okay, where it grows and grows exponentially and then kind of levels off, and that's called logistic growth. And if you looked at the review already, there's a problem on there with logistic growth. It looks like this. I think I used C on the top. So this is a logistic equation, all right? And C is what is called the carrying capacity. And what I really wanted to do with your project activity thing was do something with this, but I had a tough time trying to find a simulation that would show it. But if you think about a pond with fish, goldfish, okay, and they're going to keep growing and growing and growing until at some point the pond's going to be filled. You know, and there's not going to be enough food for the fish, and then so the population is going to start leveling out. It might even decline a little bit. So that's logistic growth. Okay, so it grows, 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 and then it has some sort of carrying capacity, which is that limit. All right? So, again, they give you the equation on 24. They tell you, here's what it is. This is on a population of, I guess, eagles, it looks like. Okay, and so here's a carrying capacity, here's a constant, and there's a constant. The K is probably some sort of a rate, which it says it is. So what it says, determine the carrying capacity of the environment. Well, that's going to be about 500. This is number 24 on page 358. What is the growth rate? Well, that's going to be 16.2% because that's your K value. What is the population after 3 years? Well, put it into the equation, figure it out. Put that in the Desmos, and you would just figure that out. Okay? When would the population be 300 eagles? Well, I would probably graph it. I would probably take this equation, graph it. So I would graph this equation here. Make sure you put X for T. And then I would go next to, down below, I'd go Y equals 300 and figure out where they cross. Because that equation is going to go something like this. And this is going to be 300. And that's where I would figure out where they cross at. Okay? So that's logistic growth. So on your test, I would give you the equation for you to work with. I think the one in there, you have to figure out what K is or something like that. So it would be similar to that, but it wouldn't be any different than what we just did with Newton's law of cooling. So it'd be the same thing. What I want to do next is take some, I want to go get some, while you're braking, I want to go get some hot water and do a Newton's law of cooling thing for you. And because that'll give you a pretty good idea of how to collect some data and then find a rate and all that exponential equation. And then I want to do one more, I want to show you how to find a logistic equation using Desmos. And then we're done with anything I'm going to show you the rest of the night. Okay? So that's what I want to do. Any questions on that stuff we just did? It's a lot, but, and I know I went over way over, I usually do. Okay, but it worked out better when we did it. And I'm recording this too at the same time, even though it's not showing up on there. Oops. So when you do it by hand, you just don't get a really good, accurate feel for how that is. But if you have the Desmos actually figure out the equation, you'd get a better look at it. And that's what I wanted to show you how to do. Okay, so here's how we're going to do it. We're going to come down here to this thing here, all right, to this line. So a logistic equation has that C for carrying capacity, 1 plus A times E to the negative KT. That's what the equation is. So I'm going to go Y, but I'm going to go 2. All right, and I do Y2 because that's what the name of this column is in this table. All right, so now I'm going to go equals, and now I'm going to type in, oh, not equals, dang it, sorry. I need tilde. ABC, where is it at? Right here, tilde. So now I'm going to type in that logistic. So I'm going to go C divided by parentheses. Let's put it down there already. 1 plus A times E to the K X1. All right? I wonder if it needed to be a negative K. Let's try putting a negative up there. See if it likes that better. Why isn't it? Oh, it's got to be X2. That's why. I was wondering, what the heck? X2. There we go. Okay. So, man, that's nice. See how it fits that real nice there? Okay, and we'd have had to, if we'd have been guessing at these, we could have guessed along. They might have not given us a very good picture of it. All right. So C, there's your carrying capacity, about 135. Rates 0.36, and 21.55 or whatever is the constant. All right. So what you want to do is you want to go into another line of Desmos. We're going to type Y 1 or 2, depending upon your data. Make sure you get that tilde. C divided by, and it's going to put it on the bottom. So then you're going to go 1 plus A E negative KT, or K, sorry, X1 or X2, and then it will give you the equation, okay? That's how you do it, and I kind of recorded it a little bit here too, although you're not going to see the Desmos part of it, all right? Any questions on how we just did that? That's like the last problem, I think. I wanted to show you how to do it so you know how to do it.
So we don't have to do it by hand?
The second to last problem, I'm pretty sure how you do it by hand. And then, like I said, after that, go ahead and find let Desmos do it, so you got to do it kind of both ways. I'm pretty sure it kind of leads you to doing it by hand, and that's how I remember it. I don't have one in front of me, so. Anything else on that? All right, let's see how our, I can come back to if somebody else wants to see it, what we got going here. Okay, so there's our data. Look at that. So that is a nice little exponential decay. And let's take a look at the data here. I think we can put it in a table. There it is. All right. Trying to get over to the other. It used to be tab to get over to the other side. Is it this guy? This guy? Oops. Come on. Oh, there it is. I can't. Oh, here I know what to do. Okay, so there's your data right there. Okay. So if we wanted to find an equation for this, does anybody remember how? I hope you can, sorry, maybe here. Can we see this a little better? Let's see if I can zoom in here.
We need the initial temperature, the room temperature, and then the amount of time that it was sitting.
Yeah, I'm trying to zoom in so you guys can see it better. There we go. Okay, so we have the initial temperature, right? Okay, and then what were you saying, Jess?
You need the initial temperature, the ambient temperature, so like the temperature constant for varsity.
Well, we don't. I can't do Newton's law of cooling. So I don't know how. I mean, well, I don't know what the temperature is here. So I just want to do a y equals a times b the x on it.
Oh,
Okay,
that's simple.
that's simple. That's what I want to do. Yeah. So how do we find? We have a. How do we find b? What are we going to have to do to find b? Divide what?
The difference of 10 and 0 by 0. 45. 45 or
So we want to find the difference in these temperatures, correct? Okay. Now you can do it that way. All right. That's not going to find b though. That's going to find your rate. Okay. So you have to be careful when you. So if you find the difference between these two, which is about 8, right, and you divide by 53.9, that's going to give you a rate, which we could do. So I could go 8 divided by 53.98, and it would tell me that's about 14. And we could do that on the next one here. Equals, difference there is about 4.7 divided by 45.9, 10%. Then I could do this one. Difference there, here I'll just figure it out. 41.2 minus 37.8, and then divide it by 41.3, and I get 0.08. Okay? I mean, we could continue to do this. There's actually a way to do it faster. .06. So that rate is, that's what happens when you're dealing with real stuff, is a lot of times you don't get a constant rate every single time. Now it's starting to get a little better. So it's maybe about 0.5. So let's do one more. So we could do that, okay? We could also just take and go and divide these two. And that would give us B. So when you divide those numbers, okay, the constant numbers, that's giving you a B. When you take the difference and subtract, that's giving you R, the rate. All right, so I'm going to do it one more time by just dividing here. .96. So I'm going to take a guess at 0.96 is a pretty good equation for it. All right, so let's try that out. So I'm going to do a graph. think I have to go menu, graph entry, edit, scatter. It's been a while since I've done one of these. Var time, var temp, go. I need 9. Okay, so there's my data again. And then I want to type in an equation. There we go. So what was that initial value? 53? Anybody remember? I think it was 53. And then that equation's point 96, I think, to the x. And I have to divide by 10 because that's what I went by. So it's not great. We'd have to play around with it some more. Oops. To get it. But you would eventually get it. Maybe a 5. Okay, it's getting a little better. So that's how that would work. So Newton's law of cooling would be better if I happen to know what the temperature in the room is, but I don't know what the temperature of the room is. Okay, we might be able to get a pretty good approximation now that that temperature thing is getting there. Let's see. I'm afraid to lose my data. Can't overwrite it. But if we could get an original, let's see if I can get that. It'll tell me what the, might be about 20 degrees, but anyway, what I just wanted to show you an example of some Newton's law of cooling. I will put the solution things up for you before I leave tonight. And